So this is the last video that's going to use a simple circuit, and then we're going to go tomorrow into more complicated circuits with multiple resistors. So if I've got a simple circuit, so a simple circuit is just one voltage source and one resistor. Boom, 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 boom. There we go. Okay. Delta VT R, and I know there's my current I. So what we're going to do here is we're going to learn the last major concept in circuits. So we've got a couple of concepts here. We've got the concept of current, what is it? The concept of potential difference, and what is it? Concept of resistance, and what is it? And then in terms of equations, we had talked about current as charge per unit time. We've talked about voltage as work per unit charge. We've talked about current as being the ratio of the potential difference to the resistance, that's Ohm's law, and then power is equal to I times delta V. Those were sort of our main notions about circuits specifically, and we can talk about how that intersects everything else we've done because power links to work over time, and you see work there as well. But what I want to really do is hone in on what's happening here in this circuit. So the first thing we're going to say here is there was a scientist, and that scientist's name was Kirchhoff, and Kirchhoff wrote two laws, so Kirchhoff's laws. So in conjunction with these two laws are super important for understanding how to intersect what's going on with circuits. And the first of Kirchhoff's laws is something that's called the junction rule. And that's not going to make any sense as a name quite yet, but it will make sense a little bit later. And what the junction rule says is it starts examining what's happening with the electrons. So here, if 10 electrons enter the battery, how many leave? Hopefully you said 10, right? And then they travel around, and those same 10 electrons go through this little bit of wire, this little bit of wire, this bit of wire. They enter the resistor, and then they leave. Because resistors don't consume electrons, and batteries don't generate electrons. It's the same electrons that are being forced around the circuit. So what the junction rule says is the current into any circuit element is equal to the current out of that element. Okay? So what that means then, or actually, let's think about where that comes from. The current in is equal to the current out. That's going back to me saying before, if 10 electrons enter this, they're going to leave. If 10 electrons enter this little bit of wire, they're going to leave that bit of wire. If 10 electrons enter the resistor, they're going to leave that resistor. Hopefully what you're thinking is then, oh, well, electrons aren't consumed. Oh, okay. So another way to think of that is that this is just really the conservation of charge. And that should make sense that charge is conserved. It's a basic law in nature, right? And so the junction rule is just the conservation of charge written for circuits. Nice and simple. So what do we get out of that? Well, what we get out of that is for the simple circuit that the current that goes through the battery, which I'll call IT, is going to be equal to the current that goes through the resistor, IR, right? Because there's only the one pathway, so the same electrons that enter this battery leave the battery, and those same electrons go into the resistor, they have to leave the resistor. So the currents are identical. In fact, at any point in the circuit, if I were to measure the current, it would be identical to the current at every other point. So let's actually talk about measuring current. So there's a device to measure current, and it's going to measure the current at one point in a circuit. That's what the device does. So how do I do that? Well, I want you to think of this device like a toll booth in a road. You don't put the toll booth off to the side, you put it right into the flow of traffic, right? So I will give a name to this idea. It's going to measure the current, and it's going to be called an, oh, I'm running out of ink there. It's going to be called an ammeter. Back when it was originally developed, it was actually called an amp meter, ammeter, ammeter. Like the P was just awkward there. It became a silent P, and then it just went away. So the word kind of shifted in terms of its pronunciation and then its spelling over the years. And our schematic symbol for an ammeter is just a circle with an A in it. And so if I wanted to measure the current, what I would literally do is just plop that thing directly into the circuit. And I could put that thing in the circuit anywhere in this circuit, and it would read exactly the same. We're going to give a name to that connection a little bit later, right? But that's how the ammeter works. So now let's talk about another rule. By the way, junction, we'll get back to the meaning of that in the next video. So the next thing that we're going to look at is something that's called the loop rule. And the loop rule says the potential gained per loop is equal to the potential dropped per loop. So what does that mean? Well, that's talking about potential difference. Okay, well, where's our potential gain? At the battery, right? So if this is a 6-volt battery, 6 joules per coulomb. Every coulomb of charge that goes through this picks up 6 joules of energy. And then it travels around, and where does it drop off energy? We said that it drops off energy at the resistor. So here you go, picks up 6 joules, drops off a certain amount of joules, goes back. Well, how much does it have to drop off? Well, according to the loop rule, all of the energy. Pick up 6, drop off 6. Pick up 6, drop off 6. Well, why does it have to happen? Well, if it didn't drop off all 6, it would have some left over. It would gain 6 more, drop off some less, gain 6 more, and then the energy carried by the electrons would spin out to infinity. And if it dropped off more than 6 joules, well, that would just clearly be a violation of a fundamental principle. What fundamental principle? Hopefully you said to yourself the conservation of energy, which is exactly what this is. Conservation of energy. So the junction rule is the conservation of charge. The loop rule is the conservation of energy. And together, they're going to help us figure out a lot of things. Now, so there we go. Now, I'm going to drop a little bit of truth here. Actually, picks up 6 joules, drops off 6 joules, right? But here's the thing, in reality, remember that all of our wires not technically, I gotta stop saying that. They actually are resistors themselves. Every structured wire is a resistor. It's just that the wires have such little resistance compared to this that it's almost irrelevant. For example, if this resistor was a 100 ohm resistor, this length of wire might only have a 0.002 ohm resistance. But not technically, actually, I gotta stop saying that. Actually, as you're going along, your charges are giving up little bits of energy, little bits of energy, little bits of energy. Then it just give up a huge chunk of energy, little bit of energy, little bit of energy, little bit of energy, and then it's back to 0. So it's constantly changing that, except that it's just massive changes at the resistors. So for sake of purpose, we're actually only looking at what's happening at the resistor. If I were to graph this and talk about the potential that a given charge had versus position over the wire, right? What I would want for this to be in a perfect world would be something like this, where it has a certain potential and it drops it off when it gets to the resistor, and then it has 0 potential, gets back to the battery. But in actuality, what that graph looks like is this. It is a slight negative slope, then it has a drastic negative slope, and then a slight negative slope down to 0, where that's the resistor, right? And we want to minimize these slopes here so that we are delivering the energy to where we want it at the resistor rather than anywhere else. Now, we can actually measure the change in potential. And so what I'm going to need is a device that does that. And so there's a device, and let's write that out, a device that measures, or I guess measures is the proper way to say it, measures the potential difference between 2 points in a circuit. Okay? I think you can probably guess what this is called based on what the other thing was called. It is called a voltmeter. Its symbol is a circle with a V in it. And so if I wanted to come back to my simple circuit, where do I do this? Well, if I want to know what the potential drop across the resistor is, I test the current before it goes into the resistor, and I test the current after it comes out of the resistor, and I compare those two things, and that's how I know potential difference. So that would be a voltmeter that would read the potential drop across the resistor. If I want to read the potential gain across the battery, boom, boom, there you go. I just put one lead before the battery, one lead after the battery, and there you go. And so that's how that works. So those are Kirchhoff's laws. Those are the two types of measuring devices. I'm just going to very quickly show you those two types of measuring devices here in a simple circuit. I've got my simple circuit here, or my bulbs here. I've got my battery set up. I'm going to close the circuit, boom, and boom. Oh, I don't have the light bulb plugged in. Boom, there you go. Remember, if it's not a closed circuit, nothing happens. And then I can measure the potential difference with my device, which I thought I knew where it was. I thought I had grabbed it beforehand. So maybe I'll do that in the next video where I can find that. Looks like that's what I'm gonna have to do. You'll come back to see this. We'll show you the measuring devices in action, and then we'll look at creating circuits with multiple batteries. Not batteries, multiple resistors.